So, in the last lecture we discussed about the Rayleigh damping, where the model was very easy to evaluate a damping matrix which is proportion of M and some proportion of K matrix. So, for a classical damping to be done for a structural problem or a model, it is essential that the damping ratio should be uniformly distributed for the entire structure. We ensure this, the uniform distribution of damping by checking damping in different modes. So, there can be a couple of interesting questions on this. One, why damping should be uniform throughout the structure? Now, the answer is very simple. If you do not allow damping, let us understand damping is dissipation of energy. Whenever energy is dissipated, there is always a loss. Essentially, the loss will be strength compromise. It can also be a damage, etc. Suppose if you do not allow damping uniformly for the entire structure, which is a prerequisite of a classical damping, you are unnecessarily promoting the local damage. If the damping in the first mode is very high compared to that of the second and third mode, we all know that the mode shape will have an indication of relative position of mass points in the given system under lateral forces. So, in the first mode, all responses or all mass positions is displaced from the equilibrium position either to the positive or to the negative, either to the right or to the left of equilibrium position. So, if the damage is maximum in this first mode, the mass which is displaced by the maximum amount will invoke the maximum damage, the mass displaced by a lesser amount will invoke the minimum damage. So, generally the tip displacements in a cantilever stack like this, if invokes the maximum damage, could cause instability to the entire structural system. On the other hand, if you are able to impose uniform damping, there may be a compromise of this mass position when you superimpose all the three modes, because this is to the positive, this is to the negative, this may be also to the negative, we really do not know. There may be some compromise on one or compensation of two on the other. So, the net effect of damage indices or strength compromise, when you superimpose all the modes with equal amount of damage or damping, may save the structure. So, you must ensure that damping should more or less be uniform, which is also a prerequisite of a classical damping. So, mass proportional damping alone, stiffness proportional damping alone was not establishing this factor, because experimental studies show that both of them, either capacity, do represent the actual damping phenomena. Therefore, Rayleigh combined them and suggested a model where a proportion of mass matrix and a proportion of stiffness proportional matrix damping is taken and C can be worked out, and we also demonstrated an example in the last lecture that how zeta can be distributed, and can be seen that whatever modes you consider for analysis, not necessarily all the n modes, you may consider j modes where j is less than n. So, within that given j modes we ensure that the damping ratio is proportionally equal, not exactly, proportionally equal in all the modes. So, having understood that in the last lecture, that Rayleigh's model is applicable very much for mass and stiffness proportional, because remember mass proportional is inertia dominant, stiffness proportional recentering model. One is the design aspect, one is the payload or the feed aspect. Both are important for offshore structures. Okay, we are going for a new generation of forms for deep water and ultra deep explorations, where we do not insist on having a massive system, because installation, commissioning, decommissioning becomes expensive, whereas we also want a flexible system, because I want to take the band of the frequencies or the time periods of the structure in two distinct bands, so that the excitation frequencies do not fall in this band. So, I avoid the resonating response, and by making the structure flexible even at resonance, I can always exit the resonance band easily, because there may be a damage adapted to the structure or caused to the structural member. It will exit the damage mode, but it exit the resonance mode, and the damage can be minimized. So, one is interested in anyway having a flexible system as well as mass system with a minimum payload required for drilling and exploration. So, both the models combined together has a recommended value by Rayleigh, which is very good agreement with the experimental studies which can be applied to offshore structures. Now, added an advantage Rayleigh model, Caughey developed a model in 1960. So, he has developed a model in 1960 which is an extended study of Rayleigh. So, today in this lecture we will talk about how an improvement was made on Rayleigh's damping and how the damping ratio can be ensured using a Caughey's model. Most importantly, estimating of a damping matrix at a given dynamic analysis for a structural system where the new generation forms are involved. If you got a classical form of geometry, for example, a rectangular, rectilinear structure, curvilinear, shell shaped, etc., where the geometric forms are more or less predefined, there is absolutely no difficulty in using the classical damping model, because there is always a mass uniform distribution of mass for the entire structural system, because that is how the system is generally evolved. Whereas in offshore structures the forms are very novel, okay, because we are looking for the form dominated design where we want to have a flexible system where it can be commissioned and decommissioned easily, payload cannot be compromised. So, it is actually a hybrid combination where the feed dominated form based designs are invoked for deep water and ultra deep water systems. Therefore, one cannot look for a classical method of 2 zeta omega n where damping can be more or less uniform distributed. We must ensure that by forming a damping matrix we must show that it is having an uniform distribution of damping in almost all the considered modes of analysis, not all the modes present in the system. So, considering this, let us say let the natural frequencies and mode shapes agree as follows: omega r are the natural frequencies of and phi r are the corresponding modes. So, we know k phi r can be also written as, because we know k is omega square m. Let us call this equation number 1. Now, pre-multiply this equation phi n transpose k m inverse on both sides. So, we get let us say phi n transpose k m inverse k phi r omega square r phi n transpose k m inverse m of phi r, and this is identity which can be set to for n not equal to r orthogonality. So, this implies phi n transpose k m inverse phi k phi r is set to 0, equation 2. Okay, let us do it like this. For n not equals r, pre-multiply equation 2 again, phi n transpose k m inverse square. So, initially it was to the power 1, now I am doing it for the power 2, both sides. We get re-multiplying equation 1, this equation. So, phi n transpose k m inverse square k phi r is equal to omega square r k m inverse m phi r. Okay, let us separate this for multiplication sake. This becomes identity. Therefore, phi n transpose k m inverse square k m inverse square k of phi r is omega r square k m inverse k phi r, phi n transpose. You have to multiply phi n transpose of this. So, phi n transpose omega square r and so, which can be also written as omega r square phi n transpose k m inverse k phi r, okay, which is equal to, let us say, phi n transpose k m inverse square k of phi r. Now, we know that I call equation number 2a. From equation 2, we know that equation 2 says that phi n transpose k m inverse k, phi n transpose k m inverse k, phi r and phi n transpose is 0 actually. Okay. Phi n transpose k m inverse k of phi r is 0. Substituting in equation 2a, we get phi n transpose k m inverse square k phi r is actually 0, for of course n not equal to r. So, from the given equation of k phi r equal to omega square m phi r, I keep on pre-multiplying with the first power of phi n transpose k m inverse to the second power of phi n transpose k phi inverse, etc. We keep on getting a sequence of variations which I can generalize. So, keep on doing this. Now, I can generalize this by repeating the above procedure. we can obtain a set of orthogonality relations expressing this in a compact form as below. So, what we are trying to do is we are trying to repeat this set phi n transpose k m inverse k phi r 0, we keep on getting for every multiplier of phi n transpose k m inverse 1, phi n transpose k inverse 2, n etc. So, now I can say phi n transpose CL phi r is a subscript. Okay, let me write it like this. CL phi r is 0, where of course this equation is valid for n not equals r. We are talking about orthogonality properties. If they are equal, it become 1, where CL can be k m inverse the power L of k for L equals 0, 1, 2 etc. till infinity. Now, one can ask me a question, how this is valid for 0? If you put 0, you will get the equation number 1 back again. Okay? The original where we started, you get the equation back again. Let us rewrite CL slightly in a different manner. Rewriting, okay, I will call this equation 4a. Rewriting equation 4a, CL is equal to m inverse, because it does not matter, is identity k m inverse L k. So, I expand this L for different values from 0 to infinity. I expand this, which is equal to m inverse k, then again m inverse k, because when you keep on writing this n number of times, I get k m inverse again and again, keep on clubbing them, okay, and so on. Okay. Last term will again be m inverse k, this k is there. So, you get the same term back again, which will end up in k, which will be m inverse k to the power n, where L can be infinity. I call this equation number 5. So, if you look at the difference between equation number 4a and 5, we are working again on the coefficient CL, which is derived from the set of orthogonality relations, where 4a says CL is only a multiplier, L number of multipliers of k m inverse of k, whereas here there is an m multiplier also available here, and the k is gone, because that is clubbed, okay, because one m from here and one k from here, you get L number of terms, okay, and this m is here and that k goes away, right. So, it is rewritten now. Similarly, let us hold this at this level, take another equation. Similarly, now we have been working with m and k, I want to work with k and m in a pre-multiplied order. Let us see how we will do that. We started with k phi r is omega square r m phi r. We started with this equation, which is equation number 1. I pre-multiply this with pre-multiply the above equation with phi n transpose m k inverse, both sides. This will result in a set of orthogonality relations as below. Now, you can see here when I multiply this k inverse k will become identity. Whatever I had on the RHS of this equation will all now move to the left hand side of this equation. Okay. So, you will get the same expression back again. CL will be equal to, I will urge you must do this and see, CL will be m inverse k of L. You get the same equation, but now L varies from -1, -2, infinity. So, I have got now the variation of this coefficient from minus infinity to plus infinity. Okay. I call this equation number 6. This equation number 1. So, do not write this, this is 6. Okay. Now, more general, combining equation 5 and 6, we get, let us see what do we get. CL can be written as this m is not in the multiplier. So, m out summation L varies from minus infinity to plus infinity, AL m inverse k of L. Equation number 7. When you compare equation number 7 with that of 5 and 6, the only confusion which will start coming here is what would be this coefficient for the corresponding value of L. Okay. Interestingly, this will lead to the Rayleigh's coefficient back again. See how. So, let us say CL is m L minus infinity to plus infinity, AL m inverse k of L. In the above equation, it can be seen that the expansion will have at least n terms independent in the series. So, what is the advantage of this? The advantage is now CL can be rewritten as, you will see that after certain number of cycles of L, more than n, that is n plus 1 or n, the values will be repeated. Okay. So, at least there will be n independent terms, but I am interested only to catch the independent terms. What does it mean is, if you are looking for a contribution of k and m as a damping matrix in your Caughey damping coefficient, after specific eigen number, the contribution of k and m will get repeated. So, I am not interested in knowing those contributions are repetitive on k and m. I want to know what is the independent contribution of k and m of the coefficient multiplied on C. Even Rayleigh also focused the same thing. Okay. So, I am now looking at the independent n terms in this expansion of series, and now I can say CL can be written as m expansion, leaving the negative terms. Why I am saying n minus 1? Nth term will be repetitive. Call this equation number 8, because this is same as that equation I just written for my convenience. So, we are now estimating the damping coefficient using Caughey's relationship. We started with the orthogonality principles. So, we picked up the basic equation where k phi r is omega square m phi r, because k is equal to omega square m, omega square is k by m, we know that. We picked up that, and this equation is identically equal, we know that. Okay. We pre-multiplied and post-multiplied, or pre-multiplied in both the sides by a specific value to find out for a power of pre-multiplier of m inverse k, what is the effect of the coefficient of this matrix in terms of this multiplier L and L. So, that is what we wanted to know. We understood that the series is expanding from minus to plus infinity in a broader range, but it is understood from the series that all terms in the series will not be independent. Only n terms will be independent. So, n minus 1 we want to capture from 0, we leave the negative part. Now, if I substitute L is equal to 0, I get A0 and k by m. Okay, this is more or less looking familiar to the Rayleigh's coefficient. Similarly, L1, so it is k by m, because if you say A0, this goes 1, so there is no power, etc. Let us see how this expands. So, let us pick up first 3 terms in this series. Let us consider first 3 terms in the series. So, A0 m m inverse k of 0, which is nothing but A0 m. Similarly, A1 m m inverse k of 1, which is A1 k. These 2 terms are same as that of Rayleigh, because it is summation, you got to add these terms. So, C will be actually equal to A0 m plus A1 k and so on. We already have these 2 terms in Rayleigh. Caughey extended this for one more series and see how it happens. A2 m m inverse k square will be A2 m m inverse k m inverse k, which becomes A2, okay, this is unity k m inverse k. So, now we have considered this to an n independent terms, but there is no guarantee, there is no necessity that in estimating the damping coefficient you must consider all the modes which are independent. You can truncate the modes to j, where j is less than n minus 1. So, now considering only j terms where j is less than n minus 1, which need to be included. In Caughey series. So, now C will be equal to, the damping coefficient matrix will be equal to m, L varies from 0 to j, AL m inverse k m. Call this equation number 9. That is my damping matrix. Actually need to check the zeta value in every mode, that they should be uniformly distributed. We are talking about the whole argument on classical damping applied to the structural systems. Hence, the generalized damping matrix can be given by Cn is phi n transpose C phi n, that is the generalized damping matrix, which is now written as L is equal to 0 to n minus 1 phi n transpose, instead of C it is Cl phi, where Cl is given by equation 9 if it is for j terms, or equation 8 if it is for n minus 1 terms, where Cl is m of m inverse k of L, is it not? So, for L equals 0, L equals 1, L equals 2, L equals 3, phi n transpose Cl, that is C naught phi n which can be simply phi n transpose C0 for L is equal to 0, we know it is A0 m, we just now calculated A0 m of phi n. We already know phi n transpose m phi n is A naught m n, normalized mass matrix. Okay. Similarly, phi n transpose C1 phi n is phi n transpose C1 is A1k of phi 1 phi n transpose k phi n is of course normalized k, but I am looking at this as phi n transpose k phi n, if you remember, it gives me the eigenvalues back omega square. Okay. So, I can write this as A1 omega n square of m n. Similarly, if L is equal to 2, phi n transpose C2 phi n will give me phi n transpose C2 was A2, I think this was this C2, A2 k m k inverse, A2 k m inverse k, A2 k m inverse k of phi n. Okay, k inverse n. So, A2 phi n transpose, or let us say omega square n phi n transpose k phi, which gives me A2 omega n 4 m. Now, I can rewrite this equation, because I am keep on substituting for this expression for different values of L to n minus 1, I am keep on substituting and keep on getting this L is equal to 2, 3, 4, you can keep on doing, can be written as summation L is equal to 0 to n minus 1 AL, because for L0, L1, L2 you keep on getting A0, A1, A2, there is a multiplier of omega n to the power L. If L is 0, it is there is no power, so it says omega n to the power of 2L. That is all. For L is equal to 2, this becomes 4. okay, of Mn. I call this as equation number, I think 9 or 10. My worry is to compute zeta. Okay, I want to work out the damping coefficient zeta. Now, the damping ratio zeta can be given by zeta n is equal to Cn by 2 omega n m, that is a classical expression. So, now zeta n can be given by half of this half. L is equal to 0 to n minus 1 A L. This Mn and this Mn goes away, this omega n goes up. So, omega n to the power 2L minus 1, which becomes equation number 11, which is my general expression for zeta. So, if you know zeta for every value, you can easily fill up and find out the damping matrix here, because you already know omega n's. If you really want to extend your study till the entire frequency band, or you can pick and choose j which is less than n as per your choice. Maybe you have got 10 modes, but you only want to say 3 modes, you can work out only for 3 modes and so on, you can truncate the number of modes. There are some critical observations on this equation. Let us see what are the critical problems with this Caughey damping model. There are some critical observations. Let us see what are they. The algorithm given by equation 11 given by equation 11 is ill conditioned. Now, why? Why is ill conditioned? Because the coefficients are functions of omega n to the power minus 1 if L is 0, omega n, L is 2 means 3, etc. So, you are actually missing certain frequencies in between, okay? It is not capturing all the frequencies, it is ill conditioned. 2, C matrix will be full, will be complete. You may ask me what is the beauty about this, even though M is diagonal and K is banded. It means the scheme is computationally expensive. Therefore, Caughey model is not preferred with respect to Rayleigh model. So, these are critical observations in Caughey system. So, we will take up an example in next class. and work out and see how this can be applied and how you can find the coefficients A0, A1 and A2, because you must understand ultimately Cn or the damping matrix C will be A0 m plus A1 k plus A2 of something. So, if you know the value of A1, I mean A0, A1, A2 etc., you already have the values of k and m, and easily multiply them and get C. So, our focus is to estimate a given problem, how to value this A0, A1, A2. We already have the equations for AZ, ALs etc. We compute this and show how this matrix can be obtained, how zeta can be evaluated. In the next example, we will see that. Then there is a third method of estimating damping, which is based upon the modal truncation and frequency, I mean modal participation. We will talk about that in the following lecture, so that we complete the discussion on estimates of damping. Okay. Any doubt here? So, this is the second model by which you can analytically estimate damping ratio in a given system, which is a substitute for the classical damping technique, especially applicable to offshore structures. Okay. Thank you.